Okay, so what's the big deal about motion diagrams?
I think it's a way to represent motion, but I'm not sure how to use it.
You want to try and make one? Can you think of a simple motion?
Yeah, how about someone running to catch the bus?
Sure.
Okay, so here's the guy. He's walking to the bus stop. But when he sees the bus coming, he starts to run.
He's speeding up at that point. What about when he catches up to the bus? How do we represent him just standing while he waits for his turn to board?
I guess the points just stay in the same place.
Oh, that's why the book puts numbers below each dot, so we know if the guy stands in the same place for a while.
That makes sense.
All right, let's add the numbers to our diagram then.
Wait, why did you start at 0, not 1?
I don't think it matters. The teacher uses 0 because it's the origin or something like that.
Okay, so is that all we need?
We also need to draw a line to represent the axis.
Are you sure it points to the left?
The guy is moving to the left, but the x-axis usually points to the right. I'm not sure. Does the direction of the axis represent the direction of the motion?
Well, probably not. If it did, we need to keep changing the direction of our x-axis, and that's definitely not allowed.
So, right or left?
Let me see. The textbook has examples with the axis pointing to the right, and others with them pointing to the left, so I think it's up to us.
If we choose to have it point to the left, then the velocity will be positive because it'll be pointing in the same direction as the x-axis.
Good point. Let's leave it to the left then.
Okay. How about the acceleration? Is it positive or negative?
Well, let's break up the motion. Acceleration is the rate at which the velocity is changing, so at first it's 0 because the velocity is not changing at all when he's just walking at a constant speed. And then when he starts running, the acceleration is positive because it also points to the left, like the axis.
I agree. And his speed's increasing, which means that both acceleration and velocity must be in the same direction.
Okay, let's try this one. Draw the motion diagram for the following motion. A car is moving at a constant velocity when it sees a yellow light that forces the driver to brake and come to a stop.
Okay, let me try. Here's the car moving at constant velocity. The points need to be at the same distance from each other. And as the car slows down, the points must get closer together. We also need to number the points so we can show that it stops at the end.
Oh, don't forget to draw the axis.
Oh, right, thanks.
I'd also like to practice making some graphs, just to make sure I got it. Is that okay?
Yeah, that's a good idea. Let's do it.
Let's start with the velocity versus time, because it's always simpler than the position one. Okay, so initially the car is moving fast at a constant speed. Then it slows down until it comes to a stop.
Yep, that looks right to me.
Okay, now let's try the position versus time. The car is moving to the right in the positive direction.
Are you sure it starts at the origin like that?
It can, but I think we should go back to the motion diagram and say that the origin is where the motion starts.
That's a good idea.
Oh, thank you. Okay, the car is moving at a constant speed, then it slows down until it stops.
Hold on, isn't this saying that the car gets back to the origin?
Oh, you're right. Good point.
The car has to keep moving further and further from where it started, right?
How do I draw the slowdown?
I think the line's just going to get shallower and shallower because the car is moving slower and slower.
I see. Don't forget that it levels off at the end when the car is stopped. Let's erase this wrong line. I think we got it.
Do you remember in class when the professor tossed the ball in the air and we were asked to analyze the motion? Can we review that one before we go to lunch?
Yeah, that was kind of confusing.
Okay, so when the ball leaves the hand, it's moving fast. Then it slows down. Then it's going to reverse direction and start speeding up again. Let's draw some velocity vectors in blue. Velocity is 0 at the top. And now the acceleration vectors, let's do them in red. The ball's slowing down at first, so the acceleration must oppose the velocity. The acceleration also points down on the way down because the ball is speeding up at that point.
Right, that makes sense. Velocity and acceleration must point in the same direction if the ball's speeding up. And it's gravity that's making the ball fall back down to Earth.
And at the very top, the acceleration is 0, right?
This is how I think about it. If the velocity at the top is 0 and the acceleration is also 0, then the velocity won't change. It'll stay 0 forever. It took me a while to understand it, but do you agree that the velocity points up just before the ball reaches the top and points down just after?
Yeah.
So the velocity is changing, right?
Yeah, so there is an acceleration. Okay. The acceleration is going to point down at the top just like it does everywhere else. That's the acceleration of gravity, like you said. Okay. Can we take a lunch break now?
Soon. Let's just do some graphs first. Let's start with the velocity.
Okay. At first, the ball is going fast, so the velocity is a big number. If we say up is positive, then the velocity is positive at first. The velocity will be 0 when the ball reaches the top. Then the ball speeds up again. But we have to be careful here. The velocity points down, so the velocity is negative.
I agree. The speed increases, but the velocity is negative because it points down.
And we should draw a straight line connecting the points because the acceleration is constant. The velocity changes by the same amount every time.
Oh, this looks just like the one we did in class, so we must have done it right. Well, now let's do the position versus time.
Okay. The initial position is small. Let's call it 0. The final position is the same, also 0, but at a later time. And then its highest some point in between. At first, the ball is going fast, so the graph should be steep, but then it slows down. And at the very top, the slope should be 0 because the velocity is 0. If we connect each line, we're going to get a curve like this.
Oh, that looks great, and it makes sense.
Okay, now can we take a lunch break?
On you? Sure.